and some absolutely new result here. My present affiliation is Laboratory of Theoretical Physics, Institute of Nuclear Research, Dubna, but in principle I'm from Sofia University, Department of Theoretical Physics. So first I'd like to remind you some basic things in two most important metrics related with black holes, Schwarzschild 1 and Kerr 1. I make some little changes in my notation. Rho equals this quantity, and it is convenient for me. I will use the Tirtus coordinate, which is defined in slightly more general way. So it may be used both outside the horizons and inside the horizons of Kerr black hole. Everyone knows this picture for Schwarzschild solution. This is Fronsdal-Kruskal-Shekares coordinates, and in these coordinates we have no singularity matrix, but this is more or less not very well known result that actually we can construct some invariants. One is construct using Euler topological invariant, another one is constructed using Chern's topological invariant. Actually, these things are the densities of these integral characteristics. And then we can construct using some not very complicated formulas, differential invariants, this one and this one. And therefore, I use my rho here. And you will see that this differential, first order differential invariants, in contrast to the algebraical invariants of metric, see the horizons. And they can see not only horizons, but ergo surfaces. So the horizon is not some coordinate object. It is both horizons are geometrical objects, and they are invariants. If you calculate in different coordinates, you will not see the horizons here in the metric as singularities, but you will see them in these new differential invariants. You can find the derivation in this article of mine, QCG 2010. And it turns out that one can enlarge the area of these invariants. It was shown by Slava Didenko and Alexei Matveev that the same invariants see the horizons and ergo surfaces in Plebansky-Demansky 7-parametric metric. Here we have mass, net charge, electric charge, magnetic charge, two parameters related with rotation and acceleration, cosmological constant, and so on. You can use the same invariants, differential invariants, to see the horizons in Carter-Plebansky solution or in Kerr-Newman solution. So these invariants are very useful. Their construction, I will once more show it, is proper for four-dimensional spacetimes. In more dimensions, you have to generalize these formulas, of course. And another thing which is slightly different from the one in the textbooks is this picture, which shows that speaking about ergo surface, we have two ergo surfaces, and the outer one and the inner one, you can see how they change with the parameter B, which I call bifurcation parameter. When we have extremal Kerr black hole, both surfaces contact. And for A smaller than M, this is the usual black hole case, we have this picture. And for the opposite one, we have next singularity, but in this case, instead of surface which is topologically equivalent to the sphere, we have torus for ergo surface. So we can consider all these cases together, and we will see what will happen when we start to construct quasi-normal modes. Quasi-normal modes were introduced for the first time in the classical paper by Regge-Wheeler, and with famous Regge-Wheeler radial equation. Actually, they were considering perturbations, first-order perturbations of the matrix. And in Schwarzschild metric, which is spherically symmetrical, you can divide the multiplier, which depends on the angles, and we obtain the radial equation with some well-known potential. Actually, this procedure invented by Regge and Wheeler works only for axial perturbations. In the case of polar perturbations, which was considered by Zirilli, we have the same equation with some more complicated potential. But it was shown by Chandrasekhar in 1983 that both problems are isospectral. So if you are interested only in the spectrum, you can consider only the first case, which is useful. For perturbations of Kerr metric, we have to consider Tucholsky approach, and using Newman-Penrose formalism and Kinnersley tetrads, which are shown here, I would say using cone variables for this problem, and using Newman-Penrose formalism, Tucholsky was able to derive the so-called Tucholsky master equation, which describes the first-order perturbations of Kerr metric for different spins. You here have a parameter S, which can take values of 0 for scalar fields, 1/2 for spinor fields, plus minus 1 for vector fields like electromagnetic fields, plus minus 2 for gravitational waves. And it was a miracle that Tucholsky was succeed to reduce these differential equations to two ordinary differential equations using the standard approach, this substitution. So we obtain Tucholsky angular equation, this one, and Tucholsky radial equations using standard notations in this business. And to obtain quasi-normal modes, I have to solve this system of two ordinary differential equations in which we have two complex parameters. One is the constant in angle E equation, and the other one is the frequency omega, which takes part here and here. So we have some quite complicated complex valued spectral problem for two spectral parameters. And there exists a lot of methods to solve this problem. I will discuss some relatively new one using exact solutions of both these equations. But before doing this, I can show you how to present the general solution of Tucholsky master equation using the partial solutions, partial solutions of the ordinary differential equations. This is the standard Tucholsky formula in which he was using the definite boundary conditions. The first one was boundary condition for angular equation, and Tucholsky and almost all people after him assume regularity condition for angular function, this theta S function. And for radial equation, we usually use black hole boundary conditions. This means that we are considering waves which are go into horizon or to infinity, no back waves from horizon at all. But there is some more general approach suggested in my article, and in which we can write down some most general solution of Chukovsky master equation, which does not obey any boundary conditions for the beginning. Next step is to use different boundary conditions. For example, if you use the boundary condition, standard boundary conditions for angular equation, you will get from here the standard Chukovsky formula. If you consider quasi-normal modes, you will have discrete spectrum for frequencies too, and instead of integral, you will have some discrete sum, which gives the equations which obey both boundary conditions for angular equation and for black hole radial equation. It turns out, and it was quite old result discovered by different authors in different years, that the Chukovsky radial and angular equation can be reduced to the so-called Hoyne equation. This is some standard mathematical equation with three singular points. More precisely speaking, I can say that this is confluent Hoyne equation, and it has three singular points. One is 0, which corresponds for Kerr solutions to the inner horizon, Cauchy horizon. One which corresponds to event horizon, and infinity, which corresponds to the physical infinity. Of course, the infinity is complicated singular point in contrast to the this one, which are standard regular singular points of this mathematical equation. It is curious to see that both horizons in this equation can be considered at equal foots. They both are poles of the equation. And my contribution to this problem is to use some special solutions of the Hoyne equation, which are called Hoyne's confluent functions. They are defined by this formula, and these solutions are Frobenius solutions, regular at the first point, 0 point, with respect to the variable z. You can see the basic formulas which define the mathematical conditions at the 0 point, and for the coefficients we have some recurrence, three-term recurrence relations with the coefficients which are written here. Unfortunately, we have no completely satisfactory mathematical theory of these functions, and sometimes one has to develop mathematics to do physics and to invent some new things, and I will show some tricks about that later.
How many points you have in Schwarzschild case?
The same. In Schwarzschild case, the difference is that the 0 is the Schwarzschild 0 point, 1, and the horizon is here.
No, here you said that you have two horizons and infinity.
Yes.
But what about the origin?
Yes, I understand. Let me explain in more details. In Schwarzschild solution, we have very terrible singular point for algebraic invariants. R equals 0, and we have horizon. Here in Kerr metric, R equals 0 is not singularity at all, and we have two horizons. When we transform our problem to Hoyne equation, in Schwarzschild case 0 is the all 0 in R, and point 1 coincides with the horizon. So they both in this approach are singularities of the perturbation equation. For Kerr, 0 corresponds to the Cauchy horizon, and 1 corresponds to event horizon, and that's all. So equations are the same. Moreover, you can see references and you can write down all solutions, both of the angular and radial equations in Schwarzschild case, in Kirchhoff case, and even in Zerilli case, using very, very similar formula in which enters confluent Hahn function. The only difference are the parameters. For Regge-Wheeler equation, you can see the parameters, and you see explicitly that R0 is the singularity of Hahn equation. And another is when z equals 1, so R equals 1, in some units, of course. You can see here for Tchaikovsky angular equation the parameters. Here the z variable is related with the cosine of theta angle. And for Tchaikovsky radial equation, we have some more complicated set of parameters, but the mathematical story is absolutely the same. We have regular singularities in Hahn function for z equals 0. This means, as you see here, that r equals r minus, this is Cauchy horizon. And we have singularity in Hahn function when z equals 1. And from this formula, you see that this means on the event horizon. So the singularities of the perturbation equations are at the points 0, 1, and for Tchaikovsky radial equation, they correspond to the Cauchy horizon and event horizon. For Schwarzschild equation, they correspond to R0 and horizon. I hope I answer your question. Okay, let's go. It is quite curious, and I was forced to develop somehow the theory of confluent Hahn functions because they have some very interesting properties. You can see the publication in Journal of Physics A. The main result is that for some special kind of parameters in Hahn functions, which I call delta n condition. This means that the delta parameter in general Hahn function is not arbitrary, but it has to have discrete spectrum. Actually, n is a positive integer, not fixed one. But if you have such parameter, it turns out that you can express the derivatives of Hahn function with very Hahn functions, but for another set of parameters. The formulas are written here, and these relations are quite simple. You see that the first parameter of Hahn functions stay at place, but second, third, and the fourth are translated by this n plus 1, and the fifth parameter goes to some more complicated thing, which is quadratic in m plus 1. And it was quite amazing that these properties reflect precisely the so-called Tchaikovsky-Starobinsky identities in terms of Hahn functions. So behind these identities stay the corresponding functions, confluent Hahn functions. Another very important thing for the second part of my talk is that in all these physically interesting cases, this condition is satisfied, and as a result, I can replace derivatives with the Hahn functions. This is important from practical point of view because at present, unfortunately, the only computer package which is able to work with Hahn functions is Maple. The last version is Maple 15, but now we are working on Maple 16. And here the package has big problems working with derivatives of Hahn function. So for practical calculations, it is useful to exclude derivatives and to use only the very Hahn functions. So using this, I can refer to some sentence by Chandrasekhar, who in some paper in 1976 proposed to introduce Tukhowsky functions as a new special functions in theoretical physics, and insists that they are very important and they generate a lot of interesting identities. Actually, this discovery shows that all these things are related with identities for Hohen functions as a standard mathematical functions. Some results, not very fresh, 2006, I has considered standard boundary problem for black hole, and not only for black holes, using the exact solutions and putting the standard student books boundary conditions on the exact solutions. Using Hohen functions and exact solutions and boundary conditions for black holes, we are able to reproduce the well-known quasi-normal frequencies for Schwarzschild black holes. Some of them are written here. And moreover, using Maple machinery, we can improve even these well-known exact solutions, which were obtained by different methods. For example, by continuous fraction method used by Lever for the first time many years ago. But we see that having three singular points, we can consider different singular point boundary problems. Here we have precisely standard black hole solution in the outer domain of Schwarzschild solution, but we can consider the interior waves of different spin for Schwarzschild black hole, or we can consider Kruskal-Shaker's coordinates and consider a new boundary problem with one singular point at zero, R0, and another one at R infinity. And we can produce different spectrum. Moreover, we can consider new boundary problem. Having exact solutions, I can use Dirichlet boundary conditions, which correspond to the object which is just opposite to the black hole. I can consider this problem putting at some R star Dirichlet boundary conditions, which means total reflection of the waves. No wave is able to penetrate inside the solution. In Schwarzschild black hole, we have no reflected waves. In this sense, we can consider the opposite solution. I can, using exact solutions, put this boundary condition on my solutions of Regge-Wheeler equation, and I will get the spectrum. Here we see the standard frequencies quasi-normal mode of black hole. If you use like parameter as parameter this radius r star on which total reflection of the wave will go, we will get completely different spectrum. The basic frequency is shown here. This red line gives the trajectory of the basic frequency in complex plane, omega. We have line, not dot, because we have free parameter, the radius of the reflection surface. So we see that the basic frequency of black hole is this point. If we have no black hole, we will have completely different spectrum. And it is quite interesting that inside is the black hole frequency, which depends only on one parameter, the mass of the Schwarzschild black hole. We have no free parameters in Schwarzschild solution. So we have exactly fixed parameter. But if the corresponding object is not a black hole or something like star, we can consider, and I will show some results in more general case, when some waves penetrate inside the object and some of them are reflected, but this is the extreme case when first here everything goes inside and nothing is reflected, and this is the opposite case when everything is reflected. This way I see that, and this is my opinion, the only way to see the horizon is to measure these frequencies. They depend on the boundary conditions, and for black hole we have extremely specific boundary conditions. They give precisely the frequencies here. Those frequencies depend only on the mass in Schwarzschild case. If we have observational results, we can immediately say, is this object black hole or isn't, or it is something else. Moreover, if we have measured two frequencies, we will check, is this indeed black hole, because in one frequencies we have two real parameters, because this frequency is complex one. In the second, we will know these parameters, and we will check does this frequency corresponds to the solutions of Regge-Wheeler equations for Schwarzschild black hole or not. So this is an indisputable way to know if black hole or not. In any other case, we will have some other possibilities. Here I will show some solutions for the interior domain of black hole. Here we have some potential. This is more or less studied, but I have numerical results, and we see that in the black hole interior, I mean, of course, Schwarzschild black hole interior, we have two series of frequencies which correspond to this potential. Here we have some finite well, and in it we have 7 spectral frequencies, and here we have infinite well and corresponding infinite series of corresponding waves. Here, of course, radial variable have a meaning of time, interior time, and t variable has a meaning of space variable. As I said, we can consider partial reflection of the waves, and this picture shows the behavior of the frequencies depending on the ratio of waves which go into horizon and waves which are reflected by the horizon. Of course, this is not black hole solution. We have to put on the horizon some thin reflector. But you see typical behavior of such frequencies, which is quite interesting, and the exact solutions. We see that some levels are going close, and another one are going far for different parameters. For Kerr solution, we can discuss the same things. Here we have a lot of solutions. In my article in QCG 2010, it was shown that all classes of exact solutions of Tucholsky master equation may be represented in this way. So we have 256 different solutions, and on these solutions we have to put different additional requirements: stability, boundary conditions, causality conditions, in-out properties, regularity conditions, and depending on our choice of these additional conditions, we will get different spectra. For example, this is a completely new thing for electromagnetic, for gravitational waves in Schwarzschild. There was old problem about 9th mode in quasi-normal modes. At the beginning, people were thinking that this is some algebraically special mode with 0 real part and pure imaginary integer part. You see that these numbers are ours, and the result is published in September and accepted for publications in PRD, and will appear the next week, maybe.
There is some mistake.
Yeah.
Misprint. You forget I.
Where?
For
Yeah, of course. Yeah, absolutely right. This is imaginary part, and it is more or less very close to 4. And this is more or less very close to 0. And at the beginning, using more crude calculation methods, not exact solutions as we do, people started to think that this is precisely 0 and this is precisely 4. So this must be some algebraic special mode. But we obtain new results using exact solutions, both of Regge-Wheeler equation and Tucholsky equation. And these solutions look completely different because they are they are solutions of different equation. But if A equals 0, Tucholsky equation gives us a spectrum of non-rotating black hole. So if everything is okay, we have to get the same frequencies using different equations and different Cohen functions. So we check this, and you see that up to 13 figures, we have completely right result. And for the first time, we calculate 7 figures in this. You have to put I, of course, here. So we insist that this is clear already, that this is not algebraic special mode. This is some very close to algebraic special modes here, but it is not. And the numbers are here. This is obtained by Regge-Wheeler. This is obtained by the Tucholsky equation. And I can excuse, you see here, this I. It stays at the right place. Okay. Then we can consider, and this is our last publication, the quasi-normal spectra. Sorry?
Maybe I missed the beginning of your talk, but maybe you would tell what's the difference between Regge-Wheeler and Tucholsky?
Tucholsky equation describes the Kerr black hole with rotation. As a special case, it contains the case A equals 0, which is non-rotating black holes. But equation is different in different variables, so from mathematical point of view, we have a completely different mathematical problem. Physically, this problem must give us the same result as Regge-Wheeler equation, which describes the non-rotating Schwarzschild solution. So there is some point they coincide as a physics, but not as a mathematics. And we check that everything's okay with physics. And here we are considering Tucholsky equation, radial and angular one, for electromagnetic spectrum of Kerr black holes. This is the radial spectral condition. This is the angular spectral condition. In this condition, only confluent Cohen function take place, and parameters looks terribly, but not extremely terribly. In these spectral conditions, this is simply Wronskian of 2 independent solutions. One is regular at the North Pole, another one is regular at the South Pole, and this condition ensures regularity of solution on both poles and give us spectral condition. As you see here, I have to use not only Cohen functions, but derivative of the Cohen function. And Maple is not able to work very good with derivatives of Cohen functions. Therefore, it is quite useful to replace these derivatives with the very Cohen functions using different values of the parameters, of course, as I was trying to explain. And we see something unexpected and quite interesting from physical point of view. For the first time, we can consider boundary conditions at infinity using the exact solutions. The problem, as formulated by Chandrasekhar already, is the following one. at infinity, I have two solutions. One is increasing very fast, another one slowly. And I have to kill the bigger solution. This is very complicated using numerical procedures because bigger solutions dominates in the numbers. And therefore, we decided to put this boundary condition at infinity. It was shown here, these boundary conditions, not on the real axis, but on some straight line in complex plane, using straight line in which the former big solution becomes smaller solution. And this solves the problem. But we see that for the lowest frequencies, we have very good coincidence with the odd results, which were published and obtained by Lever method. Then we have some spectrum. This is not published at all in the literature for electromagnetic waves, something like this spectrum, green and red points. We have for gravitational waves. But when we choose another line with different complex argument of R, complex R variable, we get another spectrum, this one, which is the right. And what is the problem? Actually, we have at infinity irregular singular point. And the behavior of functions is very, very complicated. So going to infinity in different paths in complex domain, we can get different problems. Actually, we discovered another thing which is not known up to now.
There is a discrete there.
So?
There is a discrete there. The diamonds are not red but green.
Diamonds are green.
But
Here we have some spectrum.
in the text you read the red diamonds.
I don't understand. What are you asking?
Red diamonds is written.
Red, yeah.
No, no, no.
Here we have some small deviations.
Там написано красные, эти самые diamonds, а на рисунке они зеленые.
Okay, let's.
Okay, let's discuss next. I don't understand the question, actually. We have discovered two different spectra for the same problem, depending on the complex path. And we have discovered that Cohen functions, of course, have branch points, and as in complex domain. And as usual, if you calculate using one branch, you will have one spectrum. If you use another branch of the in complex domain, you will have another spectrum. The main physical new problem is what spectrum we will see in the astrophysical observations. This is an open question, actually. You can see some more or less standard things. Some of these results were published in the previous articles by other authors using different methods. Some of them are original. One, for example, the evolution with main number n of the E constant is not published up to now. You can see the real frequencies for this spectra from some values of this ratio A divided by m and different azimuthal numbers. And we see that for black holes with 10 solar masses, frequencies are in this domain, which is very interesting at present because for several months we have a radio telescope at the space, radioastron, which intend to measure such frequencies. So we have a chance, unique chance, to measure these numbers, maybe. And we'll see what is the right spectrum, not only theoretically. Another thing which I will mention in short, is that in exact solutions we have a lot of simple equidistant spectra of Tucholsky equations. Some of them are written here. All they can be described by Hoehn functions. And we have some very, very interesting thing. We have different cases considering singular solutions of angular Tucholsky equations. These singular solutions describe collimated waves which are going in one direction. This is very similar to jets. So we think that using Tucholsky equation we can describe the cosmic jets. And here the very interesting thing is that using Starobinsky constants, we see that in the case of spin 1/2, this means, for example, neutrino jets or electromagnetic jets, spin 1, the constants of angular and radial equations are the same. So we are not able to fix the frequencies omega, and we have a continuous spectrum of such solutions which may describe cosmic jets. In contrast, for gravitational case, we have two independent constants and the spectrum, and we have no continuous spectrum. So following Tucholsky equation, we can say that there is a big difference between jets from some object. If we are considering neutrino jets or electromagnetic jets, and we will have no such jets in gravitational sector. Here are written the exact solutions, but you can find them in this CQG article 2010 with all details, and we can describe these solutions. Much more interesting thing is that we have calculated the spectra for jets from some object. And in this article published in Astrophysics and Space Science, 2010, we obtained for the first time these spectra. They are completely different from the spectra for quasi-normal modes. Nevertheless, we have used black hole boundary conditions. So these frequencies are frequencies of the jets from black holes, Tucholsky, as solutions of Tucholsky equation, and black hole is Kerr black hole, of course. You can see some nice pictures of the evolution of the frequencies with respect to the A parameter, and evolution is quite non-trivial. It has some loops and other things. And the most important maybe thing is that we can consider spectra for black hole solutions and spectra for next singularities. And the phase transition is shown in these figures. Here we have black hole boundary conditions. Here we have next singularities. Nothing strange happens. It turns out that for jet solutions in both cases are stable. This was quite unexpected because people usually think that next singularity gives non-stable solutions in perturbation theory. It depends on the boundary conditions. If you use jet boundary conditions, it turns out that jets from next singularities are stable. And we can see the frequencies and their evolution. Here is the precisely extremal Kerr black hole. And you see the phase transition from black hole to Kerr next singularity. Moreover, we can show some pictures of such jets obtained by our Cohen solutions. They look more or less nice, but much more nice look these things which are real. Here we can see the jet from M87, the famous jet. It is quite big, 500 light years long. Here we have seen another jet from protostellar object. It is very small, 0.3 light years. This is 1,000 astronomical units. It is in size something like solar system. And here we see how appear the maybe analogous star like our sun. So we see quite similar structure of the jets, nodes here and here, but the hypotheses in explanation of these jets, physical hypotheses, are completely different. Here it is obvious that we have no black hole. This is a small object and its mass is about 1 solar mass. Here we have a very heavy object which mass is 10 to 9 solar masses. And usually people are speaking about black holes. And this jet is considered like a jet from black holes. But is this really the case? We don't know, of course. And we can look at...
jet from black hole?
This is a long story, but in short, we have some accretion disk around black holes, and this...
From the neighborhood?
Yes, from the neighborhood. This disk is able to get energy of rotation of the black hole and to transform it to the energy to the string. This is the standard model. There are different models, but the idea is this one. Here we have no such things, of course, and surely no black holes. But we see a big similarity despite the fact that scales are very, very different. And if you look at the spectra, this is the spectra of the same object, electromagnetic spectra. This is not very good spectrum, but this is new one, the spectrum from the jet of M87. And they are quite similar, actually. So our idea is that if we have precise spectrum here and here, you have to extract the frequencies and to compare these frequencies with this one. This spectrum is generated from black hole boundary conditions. If you see these frequencies and they depend only on 2 parameters, A and M, everything's okay. This is a black hole. If here in the real life we see another frequencies which do not satisfy black hole boundary conditions, we will know that there in M87 there is no black hole. This is the main idea. So I have to finish my lecture, and I say thank you for your attention. So I'm ready to answer all questions for the time I have.
Okay, thank you very much for your very interesting talk. Questions, please? Please. Maybe you can go here to
Yes.
ask question. Or
Maybe I shall speak Russian or not?
no, better English.
Okay. What I would like to say that I have very much doubts that the quasi-normal modes themselves can be registered, because as far as I understand, they should, the amplitude behave like exponentially in time.
Yes, yes, yes.
Okay, but this means that you can hope to register these modes just very soon after the collapse and not long later.
Yes, yes.
But when the star collapsed, you have many other modes which are tails of radiation.
Yes.
And they go to zero, their amplitudes go
Yes.
Time amplitude, the behavior of amplitude
Yes, yes.
in time is the powers. The power depends on the number of spherical harmonics. So you will have a lot of other frequencies which you will register. And the exponential vanishing of quasi-normal modes, it's very difficult to observe. And besides that,
Yes, you are.
you have no electromagnetic radiation.
Of course, you are absolutely right, and I said that it is quite difficult to find such modes. But, for example, in the precise numerical calculations, in numerical relativity, we know that quasi-normal modes are well seen. And they dominate the evolution of the radiation of black holes or some systems which include black hole long time after the strong field regime. So something maybe can be seen. Most important problem.
Then you will see that power laws will dominate always on the exponential decay.
That's right. I'm not sure will we be able to see these modes. Yeah, but we can try, and the hope is that it seems that we have more precise experimental observational methods, and if we will have enough precision in these methods, maybe we will see something like quasi-normal modes in real observations, not only in numerical calculations. In numerical calculations, people see the first several modes. With
in calculations, I enjoy it.
Yes.
Yes. As well as there is a problem with the interpretation of jets solution, because I am afraid that they have a Newtonian analogy like Legendre functions of the second.
That's right. This is some.
It should be thrown away. Because you
Подождите, пожалуйста.
Yes, the theory of jets is quite not well understood problem, and actually people work in the theory of jets after the jet is formed, and they consider the spinning of the jet in the space in different and so on and so on. But the main problem is what is the central agent, how this jet appears. And our hypothesis is that the central agent generates some initial jet, which indicates, which induces the standard jets. And maybe we can see some tails from this spectra. It is clear that the creation of jet happens at, to say, 100 Schwarzschild radii. This is far from the central object, if it is black hole. So at that distance, we can expect that a strong gravitational field regime is over, and we will see more or less quasi-normal modes, and some jet in these modes. After that, this jet maybe will generate material jet from the media. But maybe we will have a possibility to see something from real observations. That's the idea. I'm not sure will be this idea successful. So thank you for the question.
Okay. Thank you very much. We have to stop our discussion.
Yeah.
And thanks for speaking again.
Thank you.
We will continue in 3 minutes